Welcome to The Explainer. Today, we're going to put on our detective hats to uncover the secret code of chemical reactions that are happening all around us. Seriously, think about it. Our world is essentially one giant, ongoing crime scene of atoms breaking and making bonds. Every single breath you take, every meal you cook on the stove, every time an engine turns over, you're witnessing this incredible phenomenon. We're going to act as investigators today to learn how to spot these changes, document them, and solve the incredible puzzles they leave behind.
Okay, let's dive into our roadmap for today. 1. Clues of chemical change. 2. The language of chemistry. 3. The balancing act. 4. When substances combine. And 5. Breaking things down.
Section 1. Clues of chemical change, spotting the signs.
Now, you might think chemistry only happens in sterile laboratories, with scientists in white coats carefully measuring neon liquids. But actually, it's a daily occurrence right in your own home. For instance, consider this. What happens when milk is left out at room temperature during a hot summer day? Or when an iron pan is just left exposed to a humid atmosphere in your kitchen sink? Well, the milk sours and curdles. That smooth iron pan develops a rough orange flake. In these situations, the very nature and identity of the initial substances have completely changed. It's not just a physical shift, like melting an ice cube that you can easily just freeze again. Whenever a brand new substance forms, we can definitively say that a chemical reaction has taken place.
But how can we be absolutely sure? Well, like any good detective, we need physical clues to prove a chemical crime or, a reaction has actually occurred. Our source material gives us exactly what to look for, so think of this as your investigator's checklist. If you observe a change in state, a change in color, the evolution of a gas, or a change in temperature, boom, you've caught a chemical reaction red-handed. These are the undeniable footprints left behind when atoms rearrange themselves.
Moving on to Section 2. The language of chemistry, decoding reactions.
So, now that we know exactly how to spot a reaction using those 4 clues, we need to learn the secret shorthand chemists use to document it efficiently. Imagine having to write out a full descriptive sentence every single time a reaction happens. Writing a long, drawn-out phrase like magnesium ribbon burns in the presence of oxygen to become a white powder called magnesium oxide, that is simply way too long for an efficient detective. We don't have time for that. As our text brilliantly suggests, the simplest way to do this is to write it in the form of a word equation. So, the crucial point is how we structure this equation to clearly show that before and after transformation. On the left side of the equation, we have our reactants. These are the original substances undergoing the chemical change, like the magnesium and oxygen. On the right side, we have our products, the entirely new substance formed during the reaction, which in this specific case is magnesium oxide. We place an arrowhead between them, pointing directly towards the products. It perfectly captures the transformation and shows the exact direction that the chemical reaction is moving.
And that brings us to Section 3, the balancing act, solving the puzzle.
Now we're getting to the absolute climax of our investigation, solving the mathematical puzzle of what we call the skeletal equation. But you might be wondering, why do we even need to balance anything at all? Well, it all comes down to the law of conservation of mass. This dictates that mass can neither be created nor destroyed in a chemical reaction. So balancing an equation isn't just some arbitrary math exercise you're assigned in a classroom. It's actually enforcing a fundamental cosmic law where no atom is ever allowed to simply go missing or miraculously appear out of nowhere.
And here is the problem we face: a skeletal equation. This is basically an unbalanced scale. It's an equation that has unequal mass on both sides. The number of atoms of each element just doesn't match up before and after the reaction. It's chaotic. It completely violates the golden rule of conservation we just learned. And as chemical detectives, we simply cannot let that stand. We have to bring order to this imbalance.
To crack this code and fix the chaos, we use a really structured procedure called the hit and trial method. Let's just walk through it, step by step. Step 1. You draw boxes around each chemical formula. And remember, you absolutely cannot alter anything inside these boxes because that would change the actual substance itself. Step 2. List the exact number of atoms for each element present. Step 3. Start your balancing with the compound that contains the maximum number of atoms. Think of it as the heaviest anchor in our puzzle. It's just the best place to start. And finally, Step 4. Pick up the remaining elements and balance them out one by one.
Let's look at how unbalanced things can be right out of the gate. Think about the reaction between iron and water. If we track the elements, the reactants on the left side versus the products on the right, it's a mess. We start with exactly 1 iron atom on the left, but somehow end up with 3 on the right.
The hydrogen atoms? Okay, they match up at 2 and 2, but then we have 1 oxygen atom on the left and a whopping 4 on the right. It is completely, totally unbalanced.
But by applying our hit and trial steps, by taking educated guesses and adding the smallest whole number coefficients in front of our boxed formulas, we reach this incredibly satisfying resolution. After balancing our heaviest anchors and adjusting the rest, we now have 3 iron atoms on both sides, we have 8 hydrogen atoms on both sides, and we have 4 oxygen atoms on both sides. The left-hand side perfectly, flawlessly matches the right-hand side.
And this brilliantly illustrates the elegant solution to our problem. We just transformed the chaotic skeletal equation into a beautifully balanced equation simply by adding those whole number coefficients. 3 molecules of solid iron plus 4 molecules of water yields 1 molecule of iron oxide plus 4 molecules of hydrogen gas. The cosmos is in harmony once again. Now, to make our final report absolutely complete, we also add these small notations to indicate physical states. You'll see an S for solid, L for liquid, G for gaseous, and AQ for aqueous, which simply means it's present as a solution dissolved in water. Adding these tiny letters gives us the ultimate, most informative picture of the exact reaction conditions, effectively turning us from amateur sleuths into master chemists.
Section 4. When substances combine, bringing things together. With the math officially solved, it's time to categorize our chemical culprits. We're going to start with reactions that forcefully bring things together. Our first major category is the combination reaction. The definition is super straightforward. It's a reaction in which a single product is formed from 2 or more reactants. A really great dramatic example from our source material is adding water to quicklime. They don't just gently mix together, they vigorously combine, often hissing and bubbling rapidly, to form a single new product called calcium hydroxide, which is also known as slaked lime. When quicklime and water combine so vigorously, they also release a massive amount of heat. Now, reactions that release heat along with their products are called exothermic reactions. And here is a fascinating connection for you. Did you know human respiration is actually an exothermic reaction? The very combination of glucose from your food and the oxygen you breathe in, the exact chemical reaction keeping you alive and giving you energy right now as you listen to this explainer, is an exothermic process.
Finally, Section 5. Breaking things down, shattering substances. We are now transitioning to the exact opposite type of chemical behavior, the decomposition reaction. Unlike a combination reaction where things merge together, a decomposition reaction is where a single reactant breaks down to give simpler products. Instead of 2 things merging to become one, a single complex substance basically shatters into many smaller pieces.
But here's the thing. Atomic bonds don't just let go of each other on their own, right? They need a trigger. They need an influx of energy to force that decomposition. These forces can be thermal, like using intense heat to break down limestone into quicklime. They can be triggered by light, like leaving white silver chloride out in the sunlight until it breaks down into gray silver metal. Or they can be triggered by electricity, like using a battery to perform electrolysis, essentially splitting water entirely back into separate hydrogen and oxygen gases. So, as we close the case file on our chemical investigation today, I want to leave you with a thought. If atomic bonds are constantly breaking and reforming all around us, and thanks to the law of conservation of mass, matter is never ever truly lost, what past lives did the atoms in your own body once have? Were they part of a rusted iron pan centuries ago, an ancient limestone structure, or perhaps a burst of magnesium light? It really goes to show the ultimate, beautiful efficiency of the universe. Thanks for joining me on this explainer, and stay curious.